Howdy, welcome to Elementary Statistics. I am Lance Curtis, and this is the lecture for section 2-2, histograms. In this lecture, we're going to introduce you to standard and relative frequency histograms, and then we'll get into making and interpreting those histograms, and we'll conclude the lecture with a look into skewness and how to assess normality in data sets. So let's get started. Histograms are essentially frequency distributions in graphical form. So here on the left we see a frequency table for IQ scores. And we have some data in the table. So there's two subjects who scored an IQ between 50 and 69, 33 between IQ score between 70 and 89, so on and so forth. Well, if we just take this information from the table and we stick it in graphical form, so there's the 2 for the 50 to 69, and then 70 to 89 has 33, so on and so forth. Then this graphical form is what we call a histogram. Histograms allow us to see the shape of the distribution of the data. And by that, what I mean is we're basically drawing a line that connects the top of the columns that you see there in the histogram, and that produces a shape that describes the distribution of the data. So if we connect the tops of the columns in the histogram that you see here on the screen, you get a shape that looks something like this. This shape tells us about the underlying distribution of the data. Relative frequency histograms work essentially the same way. It's just that you're using relative frequencies instead of actual counts. So here we've got, instead of 2, we've got 2.6%. And then instead of 33, you've got 42.3%. But the thing to notice with the relative frequency histogram is that the shape of the distribution of the data remains essentially the same. It's unchanged. So it doesn't matter whether you're reporting counts or percents, the shape of the distribution is going to be the same. There are ways to interpret the histograms, and unless you're like a pure mathematician, you're not going to be doing these because they're cute. Okay? In fact, you probably won't even think they're cute. You're going to be looking for some practical application. And the practical application that we most get from a histogram is a better understanding of our data. Typically, we want to see a data set that assumes a normal distribution. And the reason for that is that many of the statistical analysis methods that we'll get into later in the course have an assumption that the data you're going to apply those methods to are normally distributed. We want that assumption to hold true so that we can use these methodologies. And that's why we often look for normally distributed data when we're doing statistical analyses. Recall that a normal distribution has that bell curve shape that you see here. So we have a distribution that starts low in value and then moves up to a high point and then comes back down again to a lower value. Notice that each half of the graph, the distribution, essentially mirrors the other. So the left side looks just like the right side flipped over, and vice versa. If we look back at the histogram that we saw on the previous two slides and notice the shape of the distribution, it roughly resembles a normal distribution. Now, of course, it's not exact. If you're looking for the mirror of the left to the right, well, here we've got 2, here we've got something a little bit lower, here we've got something a little bit higher, and there's nothing equivalent over here. That's okay. What we're looking for is approximation. And the big thing we look for with approximation is, what's the general shape? So the general shape of this curve does roughly follow that of a normal distribution, because we start low and then we come up to a high point somewhere around the middle, and then we come back down to a low point at the end on the other side. So we would say that this distribution is approximately normal just by looking at sight. Let's use straw-like measurements to practice making and interpreting a histogram. Now, we've already seen that how you get your data matters. So if we're going to use this data set, the first question we need to ask ourselves is, how did we get the data? Well, first, what happened was there were 12 standard length straws that were separated into 3 groups. So each group has 4 straws in it, and each of these groups is going to be cut into shorter lengths. So one of these groups was cut in half, and then a second group was cut into thirds, and then the last group was cut into quarters. So what this results in is a total of 36 shorter straw lengths. Then we tested different sample sizes. Okay, so for each sample size, we basically drew straw lengths randomly from the population of 36, and then we measured the length of the straw that we picked using digital calipers, and then we took an average straw length for each measurement. Finally, we proceeded the procedure for the entire population, and then we could make comparisons between samples and population, just like we were doing in class last time with the class heights. We can make a histogram of this data set if we open the straw length file that's in our StatCrunch group, load the data up, and then you'll see that there's the straw lengths for the different sample sizes. So first sample we took 3 straws, the second sample we took 6, the next we took 9, the next we took 12, and then finally we took the whole population. But we want to make a histogram for the entire population. So let's go into StatCrunch, and up at the top we're going to select Graph, and then we're going to select Histogram. When we do that, we get an options window that looks something like this. The first thing we want to do is select a column with our data. We want the data for the whole population, so that's going to be the n equals 36. Most of the rest of these boxes and fields that you see here in the options window are going to suit our purposes just fine. So we'll leave the default values for that. But there is one more we want to change, and that's down here towards the bottom under display options where it says value above bar, and then there's a little box next to it. You want to check that little box next to value above bar, and you'll see why here in a moment. Once you have that set, then go ahead and click compute, and you're done, and StatCrunch will produce your histogram. It should look something like this. You can change the bin length with a histogram, which is something that you can't readily do in StatCrunch with a frequency distribution. So the way that we were making frequency distributions with a bar graph is perfectly fine for just making a frequency distribution. But if you want to change the bar length, then what you need to do is make a histogram. The way that you change the bin length is, notice here in the options window, underneath the section titled bins, there's a field for width. Now, it's grayed out with this word optional in it because it's an optional feature. So if you leave it as is, the default setting is for StatCrunch to determine what's the optimal number of bins that you want to have to put your data into, and then it goes right along with that. However, if you want to change the number of bins, if you think that the graph would actually look better with a different number than what StatCrunch thinks is optimal, then you have that ability to do that. Keep in mind that if you increase the bin width, that results in a lower number of bins for you to put data into. Conversely, if you decrease the bin width, then that's going to increase the number of bins you have in your histogram. So you can observe what happens to the shape of your histogram when you change the bin width. So if you feel, go ahead and pause the video right here and then go back into StatCrunch and make 2 more histograms. Create one that has a bin width of 15 and then do another one that has a bin width of 5. And you can pause the video at this point, go ahead and make your histograms, and then when you get done, come on back and we'll actually talk more about those different histograms. Okay, welcome back. I hope you made your histograms. We're now ready to go on to the next step to compare what changing the bin width or length does to the actual histogram itself. So here are our 3 histograms. The one in the center with the bin width of 10 is the one that StatCrunch produced by default. The ones on the end with a bin width of 5 and a bin width of 15, these are the ones that you were asked to produce. And now let's look at comparing the distance in the shape that changes with the bin width. So notice that if we increase the bin width, we actually get fewer bins to put data into, and the data becomes more scrunched together. If you decrease the bin width, then that means you're increasing the number of bins that you can put data into. And notice how the shape of the distribution changes. So here we're actually starting somewhere in the middle and then coming up and coming way back down and then coming back up again. Here, with bin width of 10, we were coming up, down, and then, ooh, there's a little bit of a gap here, and then we come up, down, and up again. Notice with the last example, bin width of 5, we've got a real roller coaster because we've got way more bins to put data into. So the default setting in StackCrunch will generally optimize the number of bins that you want. Okay, you don't want too few and you don't want too many. You want to get, some sort of sweet spot right in the middle. But where is that sweet spot? Well, there are equations and formulas that you can actually use to determine what that optimal number is, and they've been programmed into StackCrunch. So generally speaking, it's for the most part, you're just going to want to let StackCrunch do that number crunching for you. Just go with the default and let it pick the number of bins to put your data into. If you deviate too far from that optimal number, okay, you'll see that the shape of your distribution as revealed by your histogram changes. And that's going to obscure characteristics of the underlying data. So you want to make sure you get that optimal number. And again, just let StackCrunch do the number crunching for you. Now, here's another thing to consider when you're looking at the shape of your distribution. How many populations do you think are in this data set? And how well does that compare with what each histogram reveals below? I'll give you a moment to compose your response, and then we'll go and have a discussion. Okay, so what we're seeing here in this data set are actually two populations of straw lengths. So let's look at the center example where we've got the optimal number of bins where the bin width is 10. This gap right here is revealing a separation between our two populations. So these 8 straws here come from the 4 straws that were cut in half. They're going to have longer straw lengths than the ones that were cut into thirds and the ones that were cut into quarters. And you can sort of see here, you've got the 3 and the 9 and the 6 and the 10. And if you add that up and think about, okay, so how many straws do we have in each group and what were they cut into, you can pretty well see that here we've got quarters, here we've got thirds, and here we've got halves. But the halves are so much longer than the thirds and the quarters that they're separated out from the main group by this gap here. So there's actually 2 populations, and the big clue to that is the gap that you see in the histogram. Well, let's see what happens when you look at changing the bin width. So if you go to the bin width of 5, so you've got an increased number of bins to put data into, notice there's too much resolution. There's a second population here, and here's the main group here, but everything's kind of spread out, and it kind of looking here at this low point here kind of makes you wonder if there's not something being obscured here. There of course isn't, but it leads to the question and the suspicion that doesn't need to be aroused because there's nothing there. On the flip side, if we go to a bin length of 15, notice how there's no gap in the data set. All the data has been scrunched together. So having that change in the bin width obscured an underlying characteristic of the data, which was that there are 2 populations in the data set. So you really want to get the optimum number of bins in order to reveal what's underlying your data set. So to continue, let's actually use that default setting on our histogram so we get that optimum number of bins. What can our histogram say about the following? First, what is the approximate number of straws with a length greater than 100 millimeters? I'll give you a moment. Look at your histogram. What's the approximate number of straws with a length greater than 100 millimeters? Well, I hope you said 8 because that's the right answer. And the way we get to 8 is we come down here. Here's our lengths down here at the bottom of the graph. So we want greater than 100. So 100's right here. So anything greater than 100. So that's 3, 2, and 3. And that gives us 8 when we add those together. So the approximate number of straws with a length greater than 100 millimeters is 8. Notice we have the numbers at the top of the columns in our histogram. That's what you get when you check off that box that says value above number in the options window. And that's why I wanted you to check that off. I find it extremely useful. This way you don't have to be like looking at the top of a column that's way over here on the right and having to, okay, I got to move over here towards the axis and try to take, well, gee, is that 3 or is that what, 3.2 or is that 2.8? I don't know. If you get the number on the top of the column, then you don't have to do any of that. You just read the number off the top of the column. So I wish they would have made that the default option because it's one that I actually go through by default. So be sure to check that box whenever you're making your graphs. You'll find it very useful for answering all sorts of questions. Here's our next question here. Is that what we would expect from what we know about the population? Would we expect that there would be 8 straws with a length greater than 100 millimeters? I'll give you a moment to compose a response. Well, I hope you said yes, because that's the right answer. And the reason why we would expect that is because, as we noted earlier, there's this gap separating 2 separate populations. And noticing that if we're looking at straw lengths greater than 100 millimeters, we're looking at that group that was actually cut in half. Well, how many straws were cut in half? There were 4 straws in the group that was cut in half. And so if you cut that group in half, you end up with 8 straws. So we would expect there to be 8 straws with a length greater than 100 millimeters. What is the class width in this histogram? I'll give you a moment. And I hope you said 10 because that's exactly what we're looking at here. So here we've got 50, 60, 70, 80, 90, 100, 110, 120, 130. The class width is going to be 10 because you just subtract the lower bound from each column, or the upper bound, whichever way you want to look at it, and there you get the class width. So 60 minus 50 is going to be 10. 80 minus 70 is going to be 10. 100 minus 90 is going to be 10. Whichever way you want to look at it, just make sure you take 2 successive values, and there you've got your class width. What are the approximate lower and upper bounds of the first class? So the first bin that we're putting data into, what's the approximate lower and upper bounds? Okay, well, I hope you said 50 and up to, but not including 60. Okay, notice the way that this is written. It's using mathematical notation. So whenever you see a bracket, that means that we're including that boundary in the range that's being described. If you see a parenthesis, that means everything up to, but not including the value of that limit. So we've got 50, and then everything from 50 all the way up to, but not including 60. And we don't want to include 60 because 60 is actually included in the next bin over. Are there any outliers in the data? Well, you should be able to look at this data set and see that very easily there are no outliers. Everything's pretty much scrunched together here with the one population. Here's the second population, and there's nothing that's really far removed from that. This is the whole of it. So yes, there are no outliers in this data set. Is there a gap? Well, I should hope I don't have to pause too long for you to answer that question. Yes, there is a gap. As we noted earlier, it's our indication that we have two separate populations in our data set. What might explain the presence of this gap? Yeah, I realized I spoke too soon. We're looking at two populations, right? So because we have two populations, the data set is separated, segregated out, as you see here, and that's how we were interpreting the gap. So there's one population of star lengths that's significantly longer than the other. Let's look at another data file that you can find in our StatCrunch group and construct another histogram. So we're going to open a file called last digit. This last digit basically is randomly selecting phone numbers from different people, and then we take the last digit in the phone number and put it into our data set. So when we do that, we're going to get a histogram that looks something like this. Notice we've got a ton of zeros and quite a few fives and a spattering of the rest of the numbers in the data in the digit set, except we don't have any sevens, so we're missing that. But wow, look at all those zeros that we've got. It's pretty high. So what can our histogram say about the following? First, does the data appear to be normally distributed? And why or why not? I'll give you a moment to compose your response. Well, no, we would not say that this data appears to be normally distributed. If you extend the line across the tops of the columns that you see here in your distribution, you don't get that characteristic bell shape. I mean, it's more of a roller coaster ride where we're going up and down and up and down, and we start with the doozy. Normally, roller coaster rides end with the doozy, right? Well, here we're actually starting with the doozy, so we still way up and then we go woo. So, no, we wouldn't say that there's a normal distribution here. Do the heights appear to be reported or measured? This is your author's way of saying, is the data falsified or is it real? Okay, well, I hope you said falsified because they're more likely to be false than real, which your author would say they would be more likely to be reported than measured. Okay, and the reason why is because you've got a disproportionately high number of zeros here. If you're picking numbers at random, and each number has an equal chance of being selected, which for all intents and purposes it generally would be if you're just picking phone numbers at random, then you should see something that's more uniform and leveled out. You shouldn't see this huge disparity between zeros and fives and everything else that's there in the data set. So this is an indication that, well, yeah, you're probably making some of this stuff up, or your selection process is not completely random like you think it is. you might want to go back and look at how you're sampling your data. Let's talk for a moment about skewness, and this is a topic that just slays me. It absolutely slays me, because the way that I was using this when I was working in industry is completely backwards from the way that your author explains it. But then I remind myself that the author of your textbook is a pure statistician, and therefore he's probably going to think backwards about a few things here and there. This is definitely one of those instances where I think the thinking on this is backwards. So let me just explain what we're doing with skewness. Normally, when you see a normal distribution, you've got this characteristic bell shape like you see in the middle. And that's what we really want to see. There's no skewness to the data. But if you shift the data one way or the other, so if you shift the data here over to the left side of the graph, that creates this longer tail here on the right. And conversely, if you take the data and shift it over towards the right side of your graph, that creates this longer tail here on the left. Okay? Well, this is what we call skewing data. And a data distribution has skewness, or is skewed, when you have one of these longer tails on one side of the distribution. So the convention that's used by statisticians is that data is skewed to the right. When it's positively skewed, it has a longer right tail. Okay? They're looking at where's the longer tail in the distribution. So this distribution that you see on the right side of your screen is what they would call positively skewed, or skewed to the right. Conversely, data is skewed to the left when it's negatively skewed, or the longer tail is there on the left side. So the longer tail is over towards the negative direction, therefore it's negatively skewed. Now, this is what absolutely slays me, because when I was working in industry, my associates and I were always looking at where is the data on the graph. So if you look at the one on the left, the one that a pure statistician would say is negatively skewed or skewed to the left, my associates and I in industry would look at that and say, this is obviously skewed to the right, because where did the data shift? We wanted to see something where the data was in the center, but it's not in the center, it's shifted to the right. So we would say that this distribution is skewed to the right, and conversely, the one over here on the right is skewed to the left because the data is shifted over to the left. We're looking at the data. Your author is looking at where's the tail, the longer tail that's formed from skewing the distribution. And so when you're working your homework problems, try not to get confused with this. Just use your author's convention and you'll go out okay. Okay? To me, it just seems more intuitive to look at where's the data moving on your graph. So realize that in the real world, there are different conventions for how this sort of thing is used. But for the purposes of your homework assignments and whatnot for this class, I would suggest looking at where's the longer tail. If the longer tail is on the right, then it's over in the positive direction, so therefore it's positively skewed or skewed to the right. If you have a longer tail on the left, then that longer tail is in the negative direction of the graph, and therefore the distribution is negatively skewed or skewed to the left. We've been looking at assessing normality up till now just by doing a visual inspection of our histogram. But as you can see, if you change the number of bins in your histogram, that can affect the shape of your distribution. So simply looking at it to determine whether or not you have normality is not completely objective type of assessment. If you want something that's truly going to test it in a more objective fashion, what you need to do is construct a normal quantile plot. Okay? A normal quantile plot is also called a normal probability plot. This is a specific type of QQ probability plot. So there's all different types of plots you can make to assess different aspects of your distribution. And those plots are called QQ probability plots. The one that's specific for assessing normality is called a normal quantile plot. So basically what this does is it determines how well a given data set matches a specific distribution. So the normal quantile plot tests your data set to see how well will this fit inside a normal distribution. There are ways to interpret the normal quantile plot. So here you have your actual distribution that you're going to test, and then you make your QQ plot, which is what you see here on the right. Notice there's a red line that comes through here. That's your line of best fit. And so it's fitting the data points pretty well. All the data points you see are pretty close to the line. There's no real patterns that you're seeing with the data points. They're all conforming pretty much that straight line. And so that's what we would say would be the test for normality. Now, of course, there's numbers that are attached to this, but you can look at this and say pretty well that, yeah, those data points are lying pretty close to that line. Therefore, we're saying that our underlying distribution would fit a normal distribution. Sometimes you get data that looks like this in your QQ plot. So here's your line of best fit, which is a straight line here, but your data points are making some sort of curvature here, and they're obviously not fitting to the line here on the ends, and you even got a couple of outliers here. So here's an example where you would say that the underlying data does not fit to a normal distribution. We have a lack of normality. Here's another instance where you see lack of normality. Now, just looking at this initially, you might compare this with the example that we saw earlier and say, well, those data points aren't too far away from that line of best fit. So yeah, I would say that that's a normal distribution for our data set. But look again, notice how the data points, if you connect the dots, notice how they're making a sinusoidal shape. Okay, where at one point they're below the line, and they're above the line, below the line, above the line, below the line, above the line. So that sort of squirrely sinusoidal shape pattern is indicating a lack of normality. You don't want any sort of pattern with your data points. You want them to be roughly close to the line of best fit without making any sort of pattern. So here's another example where our data set lacks normality. Remember that the line of best fit should always have a positive slope. So as you're looking at the graph and reading it like you would a book from left to right, the line should go up as you go from left to right. If your line doesn't do that, then there's some error that's made in constructing the plot. Now, generally speaking, you're going to be using technology software to make these plots, and they pretty much do it right every time. So you're not going to have to worry about making an error like that. But for if you ever run into a plot that was constructed the old school style, then yeah, you might want to be on the lookout for that sort of thing. So let's test the normality of our last digits data set. And again, looking at the test by the eye is subjective. So we're going to make a normal quantile plot to test normality. And we're going to use StatCrunch to do that. So inside StatCrunch, under Graph, notice that one of the options says QQ plot. So the normal quantile plot that we're looking for is a special type of QQ plot. So you're going to select QQ plot from the drop-down menu. Here's the options window that comes up when you select QQ plot. So we're going to select our data. There's only one column to select from, so we have to select it, last digit, and then all the other defaults are fine for our purposes. So let's go ahead and just click compute. And when we do, we get this sort of thing that comes out. Okay, so first of all, you can actually see that the data itself is categorical in nature because all of your data points are appearing in rows, separate rows on your graph. And of course, when they're comparing on rows, they're not going to fit that line of best fit very well. And so, therefore, we would say, no, there's no normality here with this data set. Now, normal quantile plots can appear in one of two ways. So the first way is what you see here, and this is the default setting that you have in StatCrunch, where the normal quantiles are plotted on the x-axis, and the data set that you have is plotted on the y-axis. In the real world, many normal quantile plots are actually shown in reverse, okay, where the normal quantiles are on the y-axis, and the data that you're looking at is on the x-axis. You can access that feature in StatCrunch to switch the axes. If you come back over here to the options window and look under other options, here's a box that you can check next to normal quantiles on y-axis. If you check that box, then you're going to get the axes switched. So if you're looking at something and trying to figure out, okay, what's the normal quantile plot for this data set, you're trying to compare it with options that are given to you, but you notice the normal quantiles are on the y-axis, you've got to come back in here in this options window and make sure that this box next to normal quantiles on y-axis is checked. So here we have our data set. It's clearly not normal, so we would say that we have a lack of normality. What does our normal quantile plot say about the distribution? Is it normal? Well, no, the data are not normally distributed because the data points are not conforming to that line of best fit. How do you know the data are not normally distributed? Well, again, I just answered that question. The points in this plot do not fit to the straight line of best fit. That's all we have for this lecture. Thanks for watching. I will see you in the next video.